Hey guys, welcome to your minerals notes. First up, we're talking about what a mineral is. So a mineral has to have the following characteristics. So it has to be naturally occurring, it has to be inorganic, which means that it is going to not have a carbon and hydrogen backbone. It's got to be a solid at room temperature, which means it's also going to have an orderly internal structure. And then it also has a definite chemical composition, which means that for each of our minerals will be made of the same elements each time, or basically they're compounds. So for example, if I have halite, for example, so halite is, its formula is NaCl. So it's sodium chloride, which is a mineral that you've probably well, a compound you've heard of before. So really this is just table salt, just one big chunk of table salt, but when it's a mineral, we call it halite. Our minerals are gonna make up our rocks. So minerals are not rocks, we'll have a whole unit on rocks, but minerals make up rocks kind of like substances mixed together to make mixtures. And then mineralogy is just the study of minerals, just like biology is the study of life. Okay, so here we go. So mineralogy is heavily based in chemistry. That's why we've been doing a lot of chemistry review in class. And that's because, or part of that is related to the structure of those minerals. So like I said before, they're each gonna have like their own chemical formula, but a lot of minerals are just come from only one ion being different. So for example, I've got these two minerals that you can see are both silicates. We know that because they both end with SiO4. And we can see that they look very different, even though they both got one silicon and 4 oxygens. But phosphorite has magnesium, phthalate has iron. So just from one ion being different, or a single ion substitution, they look very different. Okay, so our minerals have their own shapes, or they form in these very specific shapes that we see here at the bottom. So for example, that halite that we were just looking at, here's another picture of it. That is the way that it grows or that it forms. And so as long as they are given enough space, then those shapes that they have, we call those their crystal forms. Luster, we have 3 categories of luster. We've got metallic, non-metallic, and submetallic. So metallic is going to be, it's going to be the color of a metal, and it's going to look shiny. So for example, so this one here, so it's like that silvery color and it's shiny, so that's what makes it metallic. This one, for example, you can kind of tell that it's shiny, but it's also like clear or colorless. So since it's not the color of a metal, we're not going to call that metallic. We're going to call that non-metallic. Then that in-between category that we call submetallic is this one. So this one's just like a really dark gray, but it's kind of shiny. So that's why we call it submetallic. It's kind of in the middle of being metallic and non-metallic. Our non-metallic minerals can also be further categorized, or we can use these other words. So if we see those are just other ways to describe non-metallic minerals. Another property of minerals, there's some examples, is its streak. So streak is just like if I were to take this entire mineral and just crush it into a powder, and I want to see what color it would be. It doesn't always match what it looks like. So instead of taking the whole thing and crushing it up, we're going to use a streak plate. So here's an example of one. So it's porcelain, it's not glazed, and you just kind of take the mineral and you scratch it across it. So for example, I've got some hematite here. It's kind of like a reddish gray. If I were to actually do it on the streak plate, we see that reddish brown color. So even though our mineral is reddish gray, the streak can be different. Our metallic minerals are going to have a darker streak, where our non-metallic minerals are going to have a lighter streak. So streak is more important than color because, as you can see here, all of these elements are corundum, which is also aluminum oxide, but each one of them has some different metals involved, and those are giving them all of these different colors. So I can't just say, oh, aluminum oxide looks red, because it could also be pink or purple or blue. Depending on what form of chromium you have, it could be red or pink. Depending on what form of iron you have, it could be yellow or green. So color isn't going to be very helpful when we're looking at a mineral, because the same mineral could be lots of colors, and there are lots of minerals that are all like pink or they're all gray. Hardness is another one of our properties, and so we use the Mohs hardness scale to determine how resistant a mineral is to being scratched or being abrasive. It's a scale from 1 to 10, 1 being the softest, 10 being the hardest. We usually are going to use tools, so like a piece of glass or this little copper piece, or even our fingernails, to determine how hard a mineral is. So if I can scratch a mineral with my fingernail, I know it has a hardness that's less than 2.5, because fingernails have a hardness of 2.5. Or maybe I can't scratch it with my fingernail, but it does scratch this little piece of copper. So now I know it's somewhere between 2.5 and 3.5. So we're going to have kind of a range for the hardness. So there's just an example there. You've got some other tools there, like a steel file, a streak plate. Those are just characteristic minerals for each of those values on the Mohs scale, but those aren't the only minerals that have those hardnesses. Cleavage and fracture. So that's our next one, cleavage and fracture. These are describing how a mineral breaks. So if a mineral breaks and it has like these nice smooth surfaces, even when I've just like smashed it with a hammer and this little piece breaks off, if it has those smooth surfaces, we say it has cleavage, and we describe it with by describing how many cleavage planes it has, or how many of those flat surfaces it has. So for example, I've got muscovite. Muscovite, if you can even see, is this really thin mineral. It's like in a sheet. So we say it has cleavage in one direction, or we say it has a sheet, cleavage in sheets. A feldspar, so for example, this one that I have in my hand, it's got this side is flat and this side is flat, but all of the other surfaces are not flat. So because it has two flat surfaces, when it broke, it has two directions of cleavage. 3 directions of cleavage is going to be more like a 3D object, and we've got these two that look pretty similar. We've got halite, that's going to be the one that's the 3 directions there, that's kind of more blocky, and then we've got calcite, which is also 3 directions, but you can see it kind of looks like a box that's been slanted. So for halite, we're going to say that that one has cleavage in 3 directions equal to 90 degrees, because we've got all these nice little 90-degree angles in here. For halite, we're going to say it has cleavage that's in 3 directions not equal to 90 degrees. So we don't have to specify exactly the degree angles here. We can just say not equal to 90 degrees because it's slanted. Here's a big piece of calcite. Again, this is how it breaks. It wasn't cut this way. So that is the type of cleavage that calcite has. 3D, not equal to 90 degrees. We see that because it's slanted. Fracture, again, this is if I don't have those nice flat surfaces. So I can get these like smooth curved surfaces. We call that conchoidal fracture. Or if I have these fibers or splinters, we say it has fracture with splinters, basically. And then a regular fracture is probably our most common. So we see that there in the middle. It's just nothing special about it, really. It didn't break off in any special way. Specific gravity is kind of similar to density. So we're comparing the weight of that mineral to an equal volume of water. So if I look at my mineral and I figure out how many milliliters of space it takes up, then I look at the same amount in water and see how heavy it is. So water has a specific gravity of 1. So if I say a mineral has a specific gravity of 2.7, that just means it's 2.7 times heavier than water, since water is only 1. Minerals, if you hear the term like a light mineral, light just means its specific gravity is under 2. If it's between 2 and 4.5, we call that an average mineral. And if it's over 4.5, we say it's a heavy mineral. Those are usually going to be our ones that have a metallic luster. These are all other properties that we can look at when we're describing a mineral or just trying to determine what the mineral is, like if we're out in nature and we want to know what kind of mineral we're looking at. I'll click on this real quick so we can see the tenebruscence. This should pop up. So this is just, like it says, it'll change color when exposed to light. So this is an example of sodalite and how it was kind of dug up and now it's being exposed to the light. Okay, so our minerals are separated into groups. So first of all, we have minerals that we consider rock-forming minerals, because some of these are just like kind of random, they stay by themselves. Some of them will come together to make our rocks. The minerals that we find in rocks are made primarily from these 8 elements that are listed here. And you'll notice that that oxygen is first and then silicon. That's super important because we know that those are big in our silicates from learning about our polyatomic ions. So we'll talk a little bit more about why that is in a moment, but that's in order of how prevalent they are in the Earth's crust. So we've got our mineral groups. So we start with our carbonates. So this just means that their formula ends with CO3, since CO3 is a carbonate. So an example of a carbonate is calcite, which I showed you before. So that was our one that was kind of slanted over. So that's calcium and carbonate. That's an example of a carbonate. There are several. Same idea with our oxides. So as long as it has oxygen as the anion or the negative ion, we call it an oxide. So hematite is an example of an oxide because it's iron and oxygen. Our sulfides, so like galena is just lead and sulfur, and that's what it looks like as in its mineral form. So galena is an example of a sulfide. Or sulfates, so I've got gypsum here. Gypsum is calcium and sulfate, and then you see a couple of waters of hydration listed there as well. SO4 is a sulfate, so gypsum is an example of a sulfate. Native elements just mean elements all on their own. So like just carbon would be diamond. Just the sulfur is sulfur as an element. It's also sulfur as a mineral. Our halides are going to have any of our halogens at the end. So chlorine, fluorine, bromine. So our halite, for example, is an example of that. Since we said that's NaCl, since it ends with a halogen, that's what makes it a halide or a halide. The silicates are capitalized because that's our biggest category. They make up the majority of our minerals. We will see the word feldspar there. You'll see each of those formulas. They all have silicon and oxygen. Notice that they all have the most oxygen and some silicon. So that's why we've got our oxygen being the most abundant and then our silicon being the second most abundant. So we've got more information just on the silicates next, as soon as we look at this real quick. So I've got carbon as a graphite, that's how the carbon atoms are arranged. If it's a diamond, then they're arranged this way. So still both carbon, but just different structures. So our silicates, as we know, are based on silicon and oxygen, and they're based on 1 silicon, 4 oxygens. We call that a tetrahedron, since tetra means 4. So I can see in my picture here that I've got 1 silicon in the middle surrounded by 4 oxygens. That's the basic building block or the unit of a silicate. And so sometimes I've got them like individually, they can form a single chain, a double chain, sheets, three-dimensional networks. So that's why we have so many different types of silicates. So one example would be quartz. So that's actually one silicon and two oxygens. This is a rose quartz, it's pink. And then our feldspar. So we've seen this earlier, but we didn't really call it a feldspar then, I don't think. This is a potassium feldspar. So it's another example of a silicate with that silicon oxygen tetrahedron being the basic unit. So our, oh my goodness, why? Here we go. So usually it's not just gonna be silicon and oxygen, they'll probably have something else like we said before, sodium, calcium, potassium, and that is just going to be determined by whatever was in the molten rock and those conditions when the molten rock was able to crystallize. So by looking at a feldspar, that just gives us clues as to what it was like when it formed. So minerals, we've already looked at a little bit in class, how they're used daily. Our resources include the ones that we can actually mine and the ones that we can't currently recover for profit, but maybe in the future with more technology we could. So we call ores are just any of those resources that we can actually mine for profit, and those are usually metallic. And then we also use our non-metallic minerals for like it says, paving roads, abrasives like sandpaper or in ceramics. And again, they have to be pretty concentrated. They have to be together in order for us to be able to profit them or mine them for a profit. If they're like randomly spread out, now I have to dig here and dig here and dig here, it's just gonna be too expensive. And then it's not really worth it because we don't get a profit out of it. All right, and there's just your map of where some of those resources are found. All right, thanks for listening, guys. I appreciate it. And have